Recording.
Okay. So we will continue yesterday's class. So for those who was not there yesterday, should know that the course of yesterday was recorded. So it's available. It's available on the WeChat group, and the slide also is available. And if you are new in the WeChat group, we will re-put the link for you. And also today's course and slide will be available soon after the course today. So yesterday, I will briefly tell what I explained yesterday. So yesterday I started with the introduction. So I said that the notion of fusion category is a categorification of a notion of fusion ring, which is quite easy. Oh, okay. So I mentioned the 4 axioms for a fusion ring, which are very close to the axiom for a finite group, but it's a bit more general because it includes also the representation ring of finite group, and in fact it includes much more than that. The fusion ring which come from a fusion category are called categorifiable, and the main problem is to decide whether a fusion ring can be categorified or not. And for so, we need to find a solution of its pentagon equation. Okay, which is quite hard. So then I provided some, I recall some key definition of category theory before starting to read the book Tensor Category. So this book. So I also put the link of the book. So the book is freely available online, and the link is also on the WeChat group. So we recalled some notion of fusion category which are not in the book, but which are we need them. So we recall what is the definition of a category, so object, morphism, and the action of a category. We recalled what is an isomorphism, what is a functor, what is a natural transformation between functor, natural isomorphism. We recalled the notion of equivalence of category, isomorphism of category. Yeah, and then we started with the book. We defined what is a monoidal category. So a monoidal category. So you have two axioms, the pentagon axiom and the unit axiom. We wrote that yesterday. And so yesterday we finished by we wanted to prove that so I will recall. Okay. So yeah, this one. So the unit axiom was, the unit axiom was that the functor of left and that's a left and right multiplication by the unit 1, like that, L1 x 1 tensor x, and for the right R1 x tensor 1 are auto-equivalence on C. And so the lemma we want to prove now is that lemma there are natural isomorphism L between L1 and the identity of C and R1 and the identity of C. Okay, so as I said, qu'est-ce qu'il y a? Déconnecté. Ah. Non. Tu t'es. Non, c'est bon. Ouais. C'est bon? Okay. Okay. So as I said, as I said yesterday, an equivalence of category is not necessarily an isomorphism. But here we prove that these two equivalence of category there is a natural isomorphism between them and the identity. But it's not the identity in general. So how to prove that? So we will prove that. We will prove. Qu'est-ce qu'il y a? J'entends pas. We will prove that for L. So we will prove this case, and this case is completely similar. So we will prove that for L only. Yeah. R is similar. Okay. So how to do that? So to do that, consider. In fact, we will make such an L such that we have the following commuting diagram. So you here you apply the associativity constraint 1, 1, x like that. So you have to put the inverse because in fact anyway it's if you go from there to there you have the A, but from there to there you have to A inverse. It's okay. And then you go from there to 1 tensor x, and you apply iota identity of x. So recall that iota is a fixed morphism between 1 tensor 1 to 1. It is in the axiom of the monoidal category, you fix such a morphism. So you can go from there to there. You apply iota here and you get 1, and here it's just the identity. And then here, in fact, so as I said, we want to make such an L such that if you assume this L to exist, then if you apply L1, so if you apply the functor L1 to Lx, then this diagram commute. So in particular, what we want, so we want L1 of Lx equal to iota tensor identity of X composed with A inverse 1, 1, X. Okay. But as we proved yesterday, because L1 is an equivalence of category, it induced a bijection on the set. In particular, so we can call particular Lx, such Lx should be L1 inverse, and here the inverse mean only on the set. It's not so inverse on the set. On set only, not on object. Like that. Of what is above, so iota tensor identity of X, like that. So we want to prove such an L exists, and we want it to be of this form. And if it is of this form, then it must be, each Lx must be like that. So that you can make such an Lx, and now you should prove that what you get is really a natural isomorphism. Okay. So to be a natural isomorphism, okay. So Lx, so L, such an L defined by above Lx is a natural transformation if only if, by definition, so I will write something there, but if by definition, so I should also, I already said that the functor map, so it should be like that, functor map isomorphism to isomorphism. So then this is already an isomorphism. So Lx is isomorphism, okay. But we just need to prove that L is a natural transformation, and then it will be a natural isomorphism because we already know that Lx is an isomorphism. So we just need to prove that such L is a natural transformation. So by definition, we should have, so you have for all x, y, and morphism between x and y, you should have the following diagram to commute. So like that, identity. So L1 of F, L1 of Y, Ly. So I wrote I'm going very slowly, in fact. I write identity of C of X, but this is X, in fact. But because you want to show it's a natural isomorphism between two functors, it's easier to understand if you write the functor. Otherwise, you don't understand what you are doing. So you need, if by definition, you need that to commute. So you need to prove that to commute, but you know that as we mentioned yesterday, we know that this diagram commute if and only if you apply a functor, it commutes also, and an equivalence of category. It's an equivalence or just a functor? Just a functor to have the equivalence between two diagrams to commute, or just you need to be equivalent or not? The functor. Anyway. Et le functeur doit être équivalent pour que les diagrammes commutent soient une équivalence.
Non, c'est pour que ce soit une transformation naturelle.
Ok. Non, mais L. N'applique L. But anyway, so L1 is an equivalence of category. So if you apply the fact that this diagram commute is equivalent to the fact that this diagram on which you apply the functor L1 commute. But if you apply the functor L1 here, so what you get is L1 composed with L1 of X. So this is really, sorry, L1 of X, L1 identity of C of X. So I am just rewriting this, everything with L1 of F, L1 of Y, L1 Ly, 1 compose identity of C of Y. Here, L1 compose identity of C of F. Okay, so we need to show that this diagram commutes, but voilà, c'est un simple functeur, ça suffit pas. Voilà. Okay. So as to clarify, if so in general, if you have a commuting diagram, if you apply a functor, then it's also a commuting diagram, and you can come back if the functor is an equivalence of category. Here, L1 is an equivalence of category. So if you can prove that to commute, then this automatically proves that this one commutes. But in fact, the last one can be reformulated as follows. So the last one can be, so we will replace everything by what it maps to, and we will decompose this diagram into two parts, and we will see why it commutes. So the last diagram reformulate and decompose as follows. So okay, so you have L1 composition L1 of X. So this is just like that. So 1, 1, x. And then okay. And then here L1 composed with L1 of F. And so this should be like that. ID1 tensor ID1 tensor F. And then similarly, you have that. Okay. We will get, then we will reformulate this one also. So we will reformulate that and that in the same way. Here, we will write it here because we will put something intermediate. So you get 1 x ID1 F 1 y like that. And in the middle, we will play with the associativity. So here, A inverse 1, 1 x, A inverse 1, 1 y. So you just move the parenthesis like that. And to go from there to there, you just need to apply the iota morphism here and the identity here. So iota tensor identity of x, iota tensor identity of y. And here it's just ID1 F. Okay. So, and we already know. So where is it? We have this. We already know that this, the definition of that. We the definition of that is in the previous slide here. So it's like that. And this is exactly what we use to decompose the diagram. We apply that and then that. So this, the composition of that and that is exactly what we expect. This is exactly what we want. So if we can prove that this diagram commute and this diagram commute, then the full diagram will commute, and then we are done. Then this one commute, and then this one commute, and then we are done. So it remains to prove that this diagram commutes. But this diagram commutes because, but the left and right square commute because because first, so for the left, because A, you just apply the fact that A is a natural transformation, so you can say like that. Maybe it's enough. 1, 1, and empty room. So you apply. It's like if you apply here, you go from there to there, and you just move the parenthesis. So it's just an application of associativity constraint. So this, you can see this as a natural transformation. So this is a natural transformation for the left part. And for the right part, you can do like that. So, okay, is a natural transformation. Okay. And for the right part, okay, so the right part, you made it by hand. You make the right part by hand. So you compose. So you should have. So ID. So you want to prove that if you go, so the composition of this and this is equal to the composition of this and this. So the first one is like that. ID1 tensor F composed iota IDX. So this is equal. So the composition deal with the tensor product. So this is nothing but iota tensor F. And the other one you need, the other one is, so if you go from there to there, you have iota tensor ID of Y composition with ID1 F. But this one, yes, this one. So this one is nothing but ID1 because you can prove as an exercise if you want. ID of X tensor Y equal ID of X tensor ID of Y. And so this is equal also to iota tensor F. So they are equal. So they are equal here. So we are done. So it's okay. So the result follow. The result follow. Follow. So I want to mention that so this lemma is so this one was not proved in the book. In fact, this one was assumed. That was if I in the book just said we define the natural isomorphism like that. So in the book that just said we define the natural isomorphism L such that this should be satisfied, but they don't prove that you define a natural isomorphism like that. That just stated that it's true, but that did not prove that. And in fact, if you want to prove that in details, it's quite. If you want to do everything in details in category theory, it can be quickly a mess. So, so we choose to prove that in details for now because it's a good way to be more comfortable with the structure. But in the future, we may not prove everything in details, of course. Okay. So we are happy. We prove that so this autoequivalence here. Just the tensor product by one on the left. There's a natural isomorphism with the identity. So exactly the same thing can be proved for the right one. Okay. Okay. So what should I mention that here? Just for notation. Notation. L and A are called the left and right unit constraint. Okay. Okay, so now what we want to prove. Okay. Oh, c'est quand la pause maintenant?
10 minutes.
10 minutes? Okay. So proposition. So for all x, oh, for all x in C, we have L1 tensor x equal identity of one tensor Lx, R de x tensor 1 equal Rx identity of 1. So you can decompose like that. Of course, this is not true in general. Warning. Lx tensor y is different from Lx tensor Ly in general. This is not a functorial tensor. This is not a tensor functor. Tensor transformation. Yeah, anyway. Okay, so there is something to prove. This is not obvious. So proof. Okay. So we know that L is a natural transformation. So in other words, we have the following, always the same diagram. So like that, Lx identity of C. So a natural transformation between L1 L1 identity of C. Like that. So like that, X L1 of Y, Ly, identity of C, Y, identity C of F, F. Commute. So by definition of a natural transformation, we have for all objects you have a morphism Lx satisfied such that this diagram commutes. Okay, so now apply it. By it I mean the diagram. Apply this diagram to F equal LZ and X equal 1 tensor Z. 1 equals Z. Ici. 1 equals Z. So you replace F by LZ, X by 1 tensor Z, and Y by Z. What you get is the following. 1 tensor 1 tensor Z, L de 1 tensor Z, 1 tensor Z, ID1 tensor LZ, 1 tensor Z, LZ, Z, and LZ here. Yeah, so you know that this one commutes. Okay, so we are almost done now. We need to prove. So we need to prove something like that. Yeah, okay. So what you get? So we get. so this commutes of this commute. It commutes also. So yeah. So we have. So if you go from there to there, this is equal to going from there to there. So you have LZ composed with L1 tensor Z equal LZ composed with ID1 tensor LZ. But LZ is an isomorphism, so the expected equality hold. So you can simplify. So you can yeah. So you can simplify. LZ is an isomorphism. So you have this equality. So you apply LZ. Yeah, it's okay. You apply LZ inverse here and LZ inverse here, and you get the expected equality. But with Z equals X, but it's okay. So it's okay. You apply the inverse. You can apply LZ inverse. Okay. Okay. So that proves this equality, and similarly, you can prove this equality. Okay. So that's what not complicated. The next one will be a bit more tricky. So I will state the next one, and we will prove that after the pause. So the next one is a triangle diagram. Proposition, triangle diagram. For all x, y in C, the following diagram commute. So x tensor 1, y. Here you apply the associativity, and you get x tensor 1 tensor y. And if you apply here Rx tensor identity of y, so x tensor y, and here you can also apply identity of x tensor ly. So the proposition says that this diagram commute. So commute. I can write it here because commute. Okay. So the proof after the pause. After the pause. 5 minutes of pause. Voilà. Sorry. Okay. So before proving the proposition, let's remark the former definition of a monoidal category was or is a pentagon axiom plus triangle axiom. And the triangle axiom is the commutation of above diagram. But in the book we are following, they choose to reformulate the definition of monoidal category as the pentagon axiom and the unit axiom, which is a bit more easier. And then we can prove the triangle axiom from the unit axiom and the pentagon axiom. But the definition used in this course is pentagon axiom plus unit axiom. And above, prove the triangle axiom. Okay. Pentagon axiom. Okay, so how to prove that? So to prove that, we need first to draw a quite large diagram. So let's draw it slowly. So you start from X tensor 1, tensor Y. And you apply the associativity X1, 1 tensor. So the associativity here and the identity here. So what you get is X tensor 1, tensor Y. Okay. And then, so in fact, we will draw the border of the diagram will be the pentagon axiom for some specific object. So here we draw like that. Here we apply AX tensor 1, 1, Y. And you get like that. Tensor 1, tensor Y. AX 1, 1 tensor Y. X tensor 1. Okay. So we got the technical problem. Il n'y a pas moyen de retrouver le truc. Tout est... Alors ça, c'est chiant. Ça m'est déjà arrivé. Attends. Hein? Oui, bah c'est pas grave. So, my iPad logout and login and all what I wrote was removed. I don't know if I can get that back, but I don't think so. So I will redraw that. Okay. So let's restart with the proof of the triangle diagram. So I will redraw quickly what I already drew. So, 1 y et x 1 y 1 y. So we draw the pentagon axiom. This is the border of the big diagram. A x 1 1 tensor identity of y, x tensor 1 tensor 1 tensor y. Ax 1 tensor y, x tensor. Le mieux, c'est de pas faut pas le faire sur le zoom, mais il faudrait un papier extérieur. Parce que ça, c'est trop. OK. In the middle, so x tensor 1 tensor 1 tensor y. Here, identity of x et 1 1 y. And here, ax 1 1 tensor y. Okay. So this is okay. This commute, this is the pentagon axiom. But now we will put two extra objects in the middle. So we will put x tensor 1 tensor y and x tensor 1 tensor y. And this one is also associativity. Now, from there to there, you apply Rx ID 1, ID y. ID x iota ID y. Rx ID 1 ID y, and finally here ID x so ID y. Okay, so let's denote. We will denote every intermediate diagram by some letter. So this one A, B, C. I forgot one. So D, E. I forgot to put one arrow here. I, D, X. Tensor L1, 1. And as I said, the full border here, let's call it F, the full pentagon actually. So we need, in fact, what we want to prove, we will see what we want to, what we need to, the proposition is equivalent to this diagram. We will see, because L1 is a, capital L1 is a equivalence of category. So we just need to prove every other diagram, A, B, C, E, F. Okay. So okay. So F is, so F, but maybe I should, because F is not a functor, this is just a letter. So I should write like that. Not there. Okay. So F is just the pentagon action. So it's okay. What about B and C? So B and C here, you can see that we just apply the fact that A is a natural transformation. Because you see, here you move the parenthesis here, here you move the parenthesis here. So this here and here, this is just the fact that A is a natural transformation. We apply a natural transformation. So, okay. So B and C, B, C, just apply that A is a natural transformation. Okay. So now F is okay, B and C is okay. What about R? So R. So this one. Okay, so here, yeah. So here I forgot to write tensor. Here, what you see, you don't need to care about this component because you don't you just need to care because it's tensor identity of Y everywhere. So you just need to care about that, that, and that. So for A, you need to prove, you need prove that the composition of that and that is equal to that, but this is more or less a definition of R. So let's write it. So you should have okay. So you should have Rx tensor ID of 1. So this is for A. Need to have Rx tensor ID of 1 equal to IDX tensor iota compose with that. So IDS tensor iota compose with that. So ID X tensor iota composed with AX11. But but R1 of Rx is equal to Rx tensor 1, which is equal to Rx tensor ID of 1 by previous proposition or lemma. I don't remember. Where is it? Previous proposition. And Rx of is equal to ID of X tensor iota compose X11 by definition. This is a definition we defined the the natural transformation R such that hold. So this is a definition. So this equal this, and this equal this, so this equal this. So it's okay. So for A is okay. Okay. So what about E? E here. But E, you can see that E, this is exactly as for A, but for L. So it's okay also. It's also okay. Okay, so they hold the commutation of the hold. And you see that this is what we want to prove after applying the functor L1. What we want to prove is there is something you want to prove, and if you apply the functor L1, you get that. But L1 is an equivalence of category, so if you have this, then you have what you expected. So the result follow. So the result follow because L1 is an equivalence of category. Okay. 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 So what next? So we can prove another. Diagram, triangle. So next proposition, we will prove two other triangle. So for all x, y in C, the following two diagram commute. So you start. So in the triangle diagram, we have the unit in the middle. So here, if you put the unit on the left, like that. The previous triangle was the unit in the middle, but here you have the unit on the left, and you have something quite analogous. You have the analogous diagram. So you apply the commutation, the associativity. Here you apply L x tensor y. So you can remove the one on the left. And here you apply Lx tensor identity of y. So this one commutes. And also the same one for R. So you have, wait a minute. Yeah. So the triangle diagram we proved before used both the L and R natural transformation, but here the first is use L only, and the second will use R only. So x tensor y tensor 1, and then you apply the associativity x y1 x y1 idx tensor ry. So like that. So as before, we will just prove. It suffices to prove the first and the second will be the same. Let us prove the first one. The second is similar. Okay. Ok, so il reste 20 minutes. So, okay, so the proof will be as before. So we have to draw a big diagram again. Okay. So it's a proof of the first or the second one. Okay. So you start like that. X tensor 1 tensor y tensor z. You apply the associativity. So we will again draw the pentagon axiom as the border of the diagram. So now you understand. I will draw it quickly without explaining what I am doing. So like that. Ax1 tensor y, x tensor 1 tensor y, Z of X tensor A1 YZ X tensor 1 tensor A Z. And here X tensor 1 Y tensor Z. And AX 1 YZ AX 1 Y tensor Z. Okay, and in the middle you put X tensor Y tensor Z X Y Z X tensor Y tensor Z, and like that. So here Rx, so ID of Y tensor ID of Z, ID of X tensor Ly ID of Z, ID of X tensor Ly ID of Z, and finally Rx tensor ID of Y tensor Z. Okay. Okay. So I can draw. Oh yeah. And this one ID X tensor L Y Z. So similarly, we have A, B, C, D, E, and the F, the full part. So as before, F is a pentagon axiom. Okay. As before also, you have B and C, B, C, because A is a natural transformation. So you see, there is no mystery. You apply exactly as for the same. Here you apply the naturality of A for this one and this one. Yeah. You need so here need to be careful a little bit. You need to write this like that. ID X Z, Y Z with ID Y Z equal ID Y tensor ID Z. Okay. Here you need because you need to change the parentheses from here to here. So to have the same shape, you need to decompose that as IDY tensor IDZ. And then you can go from there to there. And this is okay. So this is okay. So what about what about A? What about A? A and D. So A and D, you can observe A and D here.
So if you give 15 minutes later, there's a course here.
Sure, of course. Okay. So you see, ça c'est à quelle heure ça finit?
55.
Oui, non. Ouais. So it will finish in 10 minutes. Okay. So we see that, so what about A? A, as before, you can ignore Z here, and what you get, you can observe, this is just the, the triangle axiom here, the triangle, so the one we proved before, because you see you have one in the middle here. So this is the triangle axiom. And D is also the triangle axiom, you have one in the middle. So for A and D, this is just the previous proposition we prove, A and D. Apply previous proposition. Triangle diagram. A, B, C, D. So it reminds E. So it reminds D. It reminds E. And E, you see E, you can ignore the X component. And then you have exactly what you want. You have the triangle where one is in the left. And so so then you, as before, you just apply the fact that L1 is an equivalence of category. So E, so E commute. So as I said, it remained only, so everything was deleted again. So as I said, so E commute, but E is what we want after the application of the functor L1, which is an equivalence of category. So the result follow. Okay. 10:55. Bon. We will stop here. We will stop now. So, okay, we will stop now. So the next class will be, so next week it's a holiday. Next Monday, Tuesday is a holiday. So the next class will be the week after this. Yeah, will be in 2 weeks. Yeah. So we will write all the details on the WeChat. So there will be no class next week because of holiday. So the next class will be in 2 weeks. Okay. So see you later. And if you have a question, feel free to ask on the WeChat group. So the recording video and the slide should be available soon on the WeChat group. And we will put again the previous slide also for those new people. Okay, bye-bye.